Let me run through some of the trapezoid approximation homework. So with trapezoids, our formula looks a little bit different than rectangles. Rather than width times height, it's 1/2 width times height 1 plus height 2. So and then because we're adding multiple trapezoids together, the shortcut is that I can just do 1/2 times width and identify all the heights that I want to use, but then double all the ones in between because those are all sides that are, or heights that are shared between all the trapezoids that are sitting next to each other. So for number one, the notation that's given to us, just understand that whatever is between the two notations is your function. That's your x squared, or that's your f of x. Your bound is from 0 to 2. And then your width is your n value, your number of intervals is your n value. So b minus a over n is 1/2. So my area formula is 1/2 times width. And then we have to start at our left endpoint, keep adding our width until we reach our endpoint, just like how we would if we were doing Riemann sums. We want to find each of the subintervals, and then we just plug each of these into the functions. So f of 0, f of 1/2, f of 1, f of 3/2, and f of 2. And if I were to insert them into the function, into the x squared, these would be the values that get created, and then that ends up giving us our approximation with the trapezoids. Okay, number 5, we just have to go through more subintervals because n is equal to 6. So b minus a over n, 2 over 6 is 1/3. So we always start at the left endpoint, keep adding the subinterval over and over until we reach our right endpoint. So 1 plus 1/3 is 4/3, 5/3, 6/3, 7/3, 8/3, 9/3. And then number 9, same idea. Really, if you can just find the subinterval, then everything else is going to feel the same. 1/2 times width, add up all the heights, and then double all the ones in between, and the ones at the end just only get used once. For the homework, I want to go back and finish up the notes that we didn't finish up because some of those problems I want to kind of walk through. So 4.1 notes from yesterday. Okay, so number 4, this is on back of your 4.1A handout. Number 4, if I want to go through power rule, we have to remember the restrictions that come with power rule. And the restrictions is that if I see any radicals, I have to rewrite as rational exponents. So if I see square root of x, I got to make it x to the 1/2. If I see any variable in the denominator, I have to push it to the numerator. And I have to resolve parentheses before I do power rule. So here, that's an example of this, right? I can't go through power rule until I resolve this exponent and these parentheses. So I need to FOIL this out first. So okay, so if I expand everything out, 9x squared Right? The two middle terms will combine. So remember with power rule, with antiderivative, we're going to add 1 to the exponent first. And then whatever exponent we see up here, we're going to copy that number and put it below. This is basically going to be undoing my derivative process from first semester. Okay, so 9x squared. How many terms are we going to apply power rule? Yeah, 3 times. We have 3 terms, so each term will get its own antiderivative rule. Okay, so 9x squared becomes what? 9x to the third over 3. Yep, these numbers will always match. Minus 6x squared over 2. Now, when we take our antiderivative, what's happening to every degree that we start with? It's increasing by what? By 1, okay? So what is the degree of this 1 here? This is 1, you don't see the x, but it's really 1x to what power? Not quite. 1x to the 0, because it's not showing up, right? Anything to the 0 power is 1. So this is really sitting at x to the 0 power, which means that if I take the antiderivative, what is that power going to rise up to? To the first power. Okay, you can, there's the imaginary 1 here, and then we do plus c. Okay, again, there are three terms. They technically each produce its own plus c, but if I do plus 3c, that's the same thing as a constant. So there's no need to keep track of the number of the c's. We can just kind of make it all kind of fall into the same category and just call it, well, it's just one big constant. So let's just say plus c. So this is sometimes a trouble spot for students. And the reason why is because we're so used to derivative process that when we see a constant, we usually want to take a constant and make it go to 0, right? But here, that constant, we're going to make it rise to a degree because this is the antiderivative, right? Every degree is going to rise by 1. It's not going to fall by 1 like with derivatives. Do some cleanup here. The coefficients can reduce. So 3x cubed minus 3x squared plus x plus c. Number 5. I want to do power rule, but what's getting in the way of us seeing a clean setup for us? First, there's a what? There's a denominator, right? That denominator, we can't let that be there if we want to do power rule. And there's another issue is what? The radical, right? The square root. So if I asked you to find the derivative of this, you would do this the same way. You would split up into individual fractions, right? We talked about how with derivatives, if I see one term in the denominator, I'm going to split up into individual fractions and then kind of split everything up and then handle each separately. Same idea here. I got to move that square root of x, but I'm going to do it after I've kind of split up into smaller problems. So I'm going to rewrite this as x over x to the 1/2 plus 1 over x to the 1/2, right? I've kind of taken care of my radical, but I just want to split this up first. Anytime you have multiple terms up in the numerator and one term in the denominator, you can always split up into smaller problems. So now I can kind of individualize each term and bring each of the x up. So if this x to the 1/2 comes up, what does it become? It becomes what? X to the negative 1/2. Now this one also moves up, but it's going to have its own space. So that's just set up and ready. But this is not quite ready. We got to resolve this before we do power rule. So how do we handle this? How do these combine? What do we do if we multiply bases? Add exponents, right? There's a hidden 1 here. There's a negative 1/2. If I combine those, I get what? X to the 1/2. So now I'm ready to do power rule twice. Now, technically, I don't have to write this out twice with separate integrals or separate notations, but I just wanted to kind of
help us visualize that, yes, these are really two separate problems. You're just going to handle them individually and take care of the antiderivative individually. So this one gets its own power rule. This one gets its own power rule. So what's my new exponent? X to the 1/2 becomes x to the 3/2, right? I add 1 to the exponent plus 2 over 2. I'm going to show that what I'm doing here, I'm going to add 1, which matched up with the common denominator is really plus 2 over 2. So this becomes x to the what? 3/2 divided by, yeah, your numerator denominator will always match, plus my exponent for my second term, plus x to the 1/2 over 1/2 plus c. Now this looks messy because I'm dividing by a fraction, so I can just bring this up and make it a what? Instead of 3/2, this is going to come up as, right, if I divide by a fraction, it's the same thing as multiplying by the reciprocal. So this becomes 2/3 x to the 3/2 plus 2 over 1 x to the 1/2 plus c. Any questions with 5? Okay, number 6, what's getting in the way from us being able to apply power rule initially? Okay, so there's 3 things that I want you to point out. Can you point out those 3 things? Yeah. Yeah, so there's 3 things that are all kind of that we have to take care of individually. We got to take care of the radical. The radical has to be converted to a rational. These variables are not in the right place. We have to find a way to bring them up to the top. And then typically it's not parentheses, but we have to merge these together, right? So any y's or x's that are multiplied together, we have to find a way to resolve those before we can do power rule. So this is technically acting as a parentheses because I have a y with another y. So I'll take care of things one at a time. Yes. No. Yeah. So this basically this is the independent variable. Yeah, this semester we don't have to worry about implicit. When we take the antiderivative, we're just largely going to remain in one variable. Yeah. So yeah, we don't have to worry about like dy dx for antiderivative. So pretend like this is an x. They're just calling this its own independent variable. Okay, we have to merge these together, right? So I have to add these exponents. So 1 plus 1/2 gives me what? 3/2. So the y's have to combine. And it's still a little out of place. We're going to push that y up to the top. So that y needs to be what? Yeah. 3y to the negative 3/2 dy. Only at this point can we do the calculus. Now we can do power rule. Okay. So now we're going to add 1 to the exponents. So plus 2 over 2. The 3 is not going to go anywhere. It's just going to kind of stay in place. What's my new exponent going to be? Negative 1/2 divided by negative 1/2, right? So my new exponent and my denominator will always match. Okay, plus c. To do some cleanup here, a negative 1/2 in the denominator is same thing as what in the numerator? Not a positive 2, but a negative 2, right? So dividing by negative 1/2 is same thing as multiplying by negative 2. So I'm just going to flip this up to the top, make it negative 2 times 3. So it ends up being negative 6 y to the negative 1/2 plus c. And I want to clean this up a little bit more. Now I have my answer. I'm going to resolve my negative exponent, push that y back to the denominator. Notice that the y comes down, but the 6 remains up top, right? that negative exponent is only influencing the y. It doesn't see the 6, so only the y is going to come down to the bottom. Okay, number 7 is a bit of a mess, but I want to take the time to go through it. This is about as complex as a power rule problem can get, but we can still go through power rule with this. So, but there's a lot of algebraic cleanup that has to occur before we can do power rule. Okay, so a couple of things that I noticed here. Couple of radicals we got to convert. Expand, we got to do some expansion. We got to bring that denominator to the top, but it looks like I'm going to have separate terms there. So I should be able to separate each individual term and then clean everything up. So I'm going to take things one at a time here. Now, the hard part of this problem is all the algebra that has to that we have to do before we can even do the calculus portion. Okay, so far. All right, I'm going to FOIL this out first. And once I FOIL this out, then I'm going to distribute the 3 through, or 3x to 1/2 through. But I'm going to FOIL this out first. So 1 minus x times 1 minus x is going to be 1 minus x plus x squared. So 1 minus 2x plus x squared. Okay, distribute through. Add exponents. So 1/2 plus 1. What's my new exponent going to be? There's a hidden 1 here, right? So 1/2 plus 1 is 3/2. Distribute this 3x through to the last term. Again, I add exponents. 1/2 plus 2 is, yeah, 1/2 plus 4/2 is 5/2. Okay, anytime I have one term in the denominator, multiple terms up top, I'm going to split up into individual fractions, and then I'm going to kind of slowly clean things up one by one. Right. One by one, I'm going to bring this up to the top. As I bring it up to the top, what's going to happen with all these 1/3 here? Becomes x to the negative, yeah. Okay, the messy part of this process is if I want to combine fractions, I have to first find what? Common denominator, right? So what's a common denominator between 2 and 3? 6, right? So it's really x to the 3/6 and x to the negative 2/6. All right, if I find common denominator. All right, 3/6, same thing as 1/2. 2/6, same thing as 1/3. So 3/6 minus 2/6 is x to the 1/6. Here, common denominator. Match up it's missing a 3, so this is 9/6 and this is negative 2/6. Okay. So 9/6 minus 2/6 is 7/6. Okay, again, common denominator. 15/6, the same thing as 5/2, right? 2 times 3 is 6, 5 times 3 is 15. So 13/6. So all that can then get us to the point where we can finally do power rule. Okay, so we haven't done any calculus yet. All this is just to get it cleaned up so that my radicals are gone, my parentheses are gone, my denominator is moved up. Okay, so now we can apply power rule, add 1 to each of the exponents. So plus 6/6 for each of these. Now, once you apply power rule, a couple of things happen. Your notation drops out, your dx drops out, and then the only thing that's going to be left is a plus c. Okay, so make sure that as soon as you apply power rule, that you make your notations drop out. Okay, so that's to indicate that, this is to indicate that, we still want to find the antiderivative. We haven't found it yet. And as soon as you find it, this notation should go away. I flip all the denominator fractions as reciprocals. Do some more cleanup here. I'm just going to multiply the numerators together. Okay, it's a lot, but I think this highlights, very important algebraic skills that we need to be able to do as far as power rule goes. This is the most, this is a rule that you're going to use the most this semester, just like power rule from first semester. So this is as hard as it gets as potential power rule, but knowing all these skills is going to be helpful from all the other problems variations that we're going to see in the future as well. So getting good with power rule is, I think, the most important rule to master because it's the rule that you're going to see the most. I forgot to print out the notes for today, so if you guys can just find any space on your handout or have a separate sheet of paper, or if you want to come up and grab a blank sheet of paper, I'm just going to do a real quick. I'll pick up anything that you pick up tomorrow, but I just want to talk a little bit about trig integrals. Okay. So again, if you need separate sheets or if you don't have a blank page, you can just come up and grab one I have up here. So I want you guys to feel, and at least initially, that that trig integrals is easy. Okay, so I really want you to kind of have that mindset of, okay, if I understand this process and if I understand trig derivatives, it should not be a complicated thing, even though it may look like it. So trig integrals. It sounds daunting, but if you know trig derivatives, you should be able to make this jump without much trouble. Okay, so I don't want you guys to overcomplicate things. So first, I want to review trig derivatives. Oh, sorry. Thank you. Now, how many trig functions do we have? 6, right? And remember, yes, last semester I had you guys memorize your trig derivatives. I had you guys put them down in 2 columns, right? So let's just write those down, okay? Oh, sorry, that's cotangent. Okay. The derivative of sine is what? Let's see if we remember them. Cosine of u times u prime. Cosine's derivative is negative sine of u times u prime. Tangent's derivative is secant squared u times u prime. Cotangents is negative, yep, cosecant squared u times u prime. We know that once we get down to these two and these two, they're just going to look at each other to find this derivative, right? Secant's derivative is, yep, secant u tangent u. Cosecant u's derivative is negative cosecant u cotangent u times u prime. So let's say I didn't tell you anything at all, okay? And if I told you that the derivative of sine is cosine. So what do you think the antiderivative of cosine is? Sine. So that's all you're doing. Antiderivative, you're starting at the right side of these derivative rules, and you're just making your way to the left side. Does that make sense? So yes, there are 6 trig integral rules, but you're just working backwards from these rules. You're not memorizing any new rules. Okay. So all I want you to do is I just want you to go from the right side to the left side. And once you do that, you've created the 6 trig integral rules that we're going to be working with a lot. Okay, so the notation is going to feel a little different, but the idea is the same. So let's explore the trig integrals now. So I don't want you to memorize these trig integrals. I just want you to use these trig derivatives and just adapt them. So for every one of these, we're going to look at the right side first. And we're just literally going to move to the left side. Okay. There's some slight adjustment, but not much. So the first one, we'll say the antiderivative of cosine of u. Now, instead of u prime, we're going to use du because du is going to be the notation for antiderivative. But cosine's antiderivative is going to be what? Sine of u, and then we're going to include plus c, right? You're not memorizing any new rules. You're just adapting them for antiderivatives. Okay. Start here. Antiderivative of secant square u du equals what? Tangent u plus c. Antiderivative of, or the integral of secant u tangent u du equals secant u plus c. Okay. Now this one gets a little trickier, but if we just look at it closely, we should be okay. I want to start on this side, okay? But I want to do the integral of sine. What do you think the antiderivative of positive sine will be? Good. So this negative has to go somewhere. So it's just going to kind of move over to the other side. Because if the integral of negative sine is cosine, the integral of sine must be a negative cosine. Okay. Antiderivative of cosecant square u du equals what? Negative cotangent. Antiderivative of cosecant cotangent is what? Negative cosecant. Okay. So this looks daunting, but if you know your trig derivatives, it should feel easy, right? Because you're just literally reading this rules backwards. Now, having said that, I will say these two give students particular trouble. Why do you think that is? Why do these two give students a lot of issues? Because we have a derivative mindset, right? We see this and our natural inclination is, oh, cosine is negative sine, right? Because we're so used to seeing that, but we're working backwards, so we have to make that slight adjustment. And then we usually think of sine's derivative as a positive cosine. So this negative feels out of place. But if you understand that you're just working backwards from these derivative rules, it makes sense, right? Cosine's antiderivative is positive sine. Antiderivative of sine is a negative cosine. So just be aware of that. When you're dealing with antiderivatives, these two are the ones that I see students make mistakes with because that negative and positive do throw students off. So just be aware. But I don't want you to feel like this is complicated because if you know these derivative rules, okay, so basically on the quiz, I just want you to write these rules down at the top of the page and you can just refer to them, right? There's no need to memorize these 6. You're just working off of the rules that you already know from first semester. Okay, there's a little bit more that I want to go over from notes, but I'll cover that tomorrow. I do want to talk briefly about how AP exam or the format that that AP uses for Riemann sums. Okay, so if you guys can turn to page 14, let's see, yeah, page 14. I want to start off with something easy. Let me see. Okay, let me go to page 17. I just want to intro this a little bit, and then I will the page 17. Page 17. So these are a table of values. We just have to find the width and height for each of the subintervals, but we don't have to plug in functions and find the y values, and it's not as cumbersome as dealing with a function with left and right Riemann sum. So part A says give middle approximation with 3 subintervals for interval from 0 to 20. So one thing is if you're given a table, do not use this. This b minus a over n is for if you're just given a function and you're not given a table. But if you're given a table, do not use this. Okay, so I see a lot of students try to force a b minus a over n for this, but each of the subintervals will most likely be different, and we're going to rely on a different set of properties to help us get our width. So interval from 0 to 20, we see 0 on the left, 20 on the right. We want to basically split into three subsets that all share the same number of order pairs. Okay, so we don't care about the width is not going to be the same, most likely. So you're going to start at the middle of the first order pair, and then you're going to span across what you think will be the first subinterval. So you see how I'm go from 0 to 8, but it spans across three order pairs. And then my second subinterval, I'm going to pick up where I left off. I'm always going to have shared order pairs. And then from 12 to 20. Do you see how the widths may not be the same, but they all see the same number of order pairs? Okay, good. So the equal subinterval is in the fact that they are both, all three are seeing the same number of order pairs. Okay. Now, the width is going to come from the first row. The height is going to come from the second row. Right. Now, to find the width, you're just going to subtract between where those two vertical lines are dropping. Okay, so what's 8 minus 0? What's the width there? 8. So put an 8 above. Okay. Ignore the middle number. We just care about the ends. Okay. What's the width there? 12 minus 8 is 4. Okay. And what is the width here? 8. 20 minus 12 is 8. Okay. Now it says give middle approximation. Now middle is in quotes, okay, because 5 is not directly between 0 and 8, but it is middle in relation to 0 and 8, right? So we're not going to find the midpoint. We're not going to find any average. We're just literally going to pick off whatever the y value is associated with quote unquote middle. So the height you're going to choose is going to be 2. Okay. 9 is not quote unquote is not directly between 8 and 12, but it is the we're only going to use the table. We're not going to introduce any new values. So the best that we can choose is a height of what? 7. Okay. 18 is not exactly between 12 and 20, but it's the best that we can use. We're only going to use what's in the table. So the height that's best used is what? 6. We're going to use rectangles. Okay, we're going to add up the areas. Every area has a width and height. So the first area is just 8 times what? 8 times 2. That's my first rectangle. Second rectangle is 4 times 7. Third rectangle is 8 times 6. Okay. A lot faster, a lot more efficient than having to go through plug-in functions. So this is not hard, but I understand it takes time. Okay, so, but I'm hoping that once we get really comfortable with this, we're going to see this over and over again. AP exams, they always give a bunch of these problems. So I think by then we'll be good. But I do understand that that for some students, it comes a little faster than for others. So we are going to take the time to kind of get used to it. Okay. I just want to introduce that to us. The width comes from the top. The height comes from the bottom. Okay. So there's a couple more things that that we have to kind of clean up on. We'll do that tomorrow, but we can start the quiz review tomorrow, quiz review Thursday, and then quiz on Friday. I'll have 2 help sessions. One help session Thursday morning, another help session Friday morning, 7:30. Okay. For homework, I'm going to push the homework out another day. Okay, so no homework tonight because I didn't quite go over everything I need to go over for this section. Sorry, come get your phones. Okay, can you see how cosecant squared is over here? The answer here is squared is going to be a negative. So you're just reading this and going backwards, and that's it. I think maybe you're looking at it.
people squared from the negative.
Yeah, exactly.